Yeah. So is my screen visible?
Yes, sir.
Yes, sir.
Okay. Okay. So this is lecture number 24, and we are discussing today the central limit theorem, and I have appended this adjective here, prepended, celebrated central limit theorem. So this is one of the most fundamental um, concepts of probability statistics, and very intriguing also. So let me proceed. The plan is to give the statement of central limit theorem very precisely, and then look at applications of central limit theorem in NLP ML as well as non-NLP ML tasks. In fact, we'll first look at a non-NLP ML task, and then we'll give a rigorous proof of central limit theorem through what is called the moment generating function. So hopefully this will brush up a lot of your probability and maybe introduce you to new concepts in probability. And feel free to interject anytime, ask for clarification. As I've said, these lectures are actually academic entertainment lectures. Okay, they are not heavy on the brain. We are supposed to enjoy these lectures, looking at the foundations, looking at applications, asking any question that comes to our mind, making any comment that comes to our mind. So central limit theorem is stated this way. Okay, let's become mathematical right from the beginning. Let xi I equal to 1 to n be n variables. Okay, and they are random variables. Sorry, I should have added random. So xi I equal to 1 to n are n random variables. Each follows a Gaussian distribution. Okay, so each variable is a continuous variable and follows a Gaussian distribution independently and identically. Okay, so the distribution of xi is not affected by the distribution of xj, and they're identically distributed. That means each of these variables have same mean of the normal distribution and same standard deviation sigma. So where could we have such situations? Okay, I'm coming to the application very soon. So these are n normally distributed variables with mean mu and standard deviation sigma. Then this is the theorem. Okay, this is the theorem that the sum of these Gaussian random variables is also Gaussian. This is the theorem. The sum of these Gaussian random variables is also Gaussian, and we know more that the mean of this new distribution, which is sum of these xi's, has mean equal to n mu. That is it is equal to the sum of the means of these n variables, and the standard deviation of this new Gaussian distribution is sigma, which is the standard deviation of each of these random variable multiplied by root n. Okay, so this is the standard deviation, which means that the variance is also sum of the variances. Okay, so this is the central limit theorem. Let me repeat this, and you just see if you have absorbed the statement. Okay, and it becomes clear when we look at the application. First of all, I take n random variables. Each of these random variable is normally distributed with mean mu and variance sigma square or standard deviation sigma. Okay. So then the theorem says that the sum of these n random variables is also a normal distribution its mean is the sum of the means of these individual normal distributions. Its variance is the sum of the variances of these individual distributions. Okay, so this is the statement of the central limit theorem. I thought I saw a question on the chat box. What is the question?
Sir, is it necessary for all the xi to be Gaussian distributed?
No, coming to that. Okay, but the basic statement of CLT is this. Okay, now let us remember what is normal distribution. The normal distribution is a bell-shaped curve extending from minus infinity to plus infinity. The area under this curve is equal to 1. The area under the curve is equal to 1. We know a few more interesting things, and those have a lot of applications. Namely, the area from minus sigma to plus sigma is about 70%. The area from minus 2 sigma to plus 2 sigma is about 95%. And most of the area is concentrated in minus 3 sigma to plus 3 sigma. So these interval values are important for us, mainly for hypothesis testing. And let's look at the equation for normal distribution. The density function is given by 1 by sigma root 2 pi e to the power minus x minus mu square by 2 sigma square. Sigma is standard deviation, mu is mean. Okay, so this is indeed the celebrated Gaussian distribution function, and fx is a density function. What does that mean? It means that I cannot ask the probability of an individual value of x. What is the probability of x being equal to 0.1, x equal to 1 or 2? That probability is equal to 0. But what is useful in continuous distributions is that you find out the probability in an interval. Okay, what is the probability of x lying in the interval a to b? So that will be the integration of this function from a to b, or the area under the curve, normal curve, from a to b. Okay, this is a very basic point. On this point, is there any question? Given the density function, we are interested in interval probabilities. Okay, not point probabilities, which cannot be, which is equal to 0. We are interested in interval probabilities. And so, 3 intervals are of prime importance: minus sigma to plus sigma, minus 2 sigma to plus 2 sigma, minus 3 sigma to plus 3 sigma. This is by way of brushing up your normal distribution concepts. Okay. Any question on normal distribution? Ask any question, okay? No question is simple. Any question? Okay. So this is the curve of a normal distribution. This is the picture of a normal distribution. This is the equation. Picture and distribution, we have to firmly remember and keep it in our mind. Now we have n variables, okay, each of which has mean mu and standard deviation sigma, and their pictures also will be like this. And what is the theorem? The theorem is that this sum also follows in normal distribution. So that is the non-trivial part. Now comes the surprise. The sum of n random variables which do not necessarily follow Gaussian distribution is also approximately Gaussian, is a Gaussian, with mean and variance being sums of individual means and variances, provided n is sufficiently large. And it has been empirically found, also theoretically proved, that if n is greater than or equal to 30, then the sum follows a Gaussian distribution. So this is the surprising part of the central limit theorem, and has profound consequences. Okay, so the sum of n random variables which do not necessarily follow Gaussian distribution is Gaussian, with mean and variance being sums of individual means and variances, provided n is sufficiently large. Okay, so this allows me to not worry about the shape and parameters of individual distributions. But one thing I'm certain, that if I take some of these individual distributions, then I will enter the realm of normal distribution along with all its machinery. That is the beautiful part. And this has a profound consequence and huge number of applications. Now let us take up one of the applications. And those of you who have been with me until now, right from the beginning of start of these probability lectures, would recall this problem. We started probability lectures on 18th July 2020, 18th July 2020. And we started these lectures with this problem. And you will, if you hear YouTube lectures on central limit theorem, you will see this particular problem coming in. Okay, this is a problem from a very classic book on probability and statistics, Sheldon's book on probability and statistics. And this is the problem which is extremely illustrative of central limit theorem. This is what you will meet in many lectures, and I am also no exception. So this is the problem. A bridge is being built. The weight it can tolerate has a distribution with mu equal to 400 and sigma equal to 40. Okay. A car that goes on the bridge has a weight distribution which also follows the normal distribution given by mu equal to 3 and sigma equal to 0.3. Okay, so these are all in same units, maybe metric ton, maybe some unit of measurement of weight. We want the probability of damage to the bridge to be less than 0.1. How many cars can we allow to go on the bridge? A very practical problem, and I had remarked many times because we lived with this problem in the beginning, quite a few lectures. So the weight the weight it can tolerate has a normal distribution, has a normal distribution, I think a normal distribution with mu equal to 400 and sigma equal to 40. And the car weight also has a distribution with mean equal to 3 and sigma equal to 0.3. We assume that car's weight distribution is also normal. Okay, and these assumptions are intuitive. Okay, these are reasonable assumptions. We will not find very heavy cars, many of them. We will not find extremely light cars, many of them. The car's weight will be a bell-shaped curves. Okay, many cars will have a weight which is within a range. Okay, and below that range or above that range, the number of cars will fall, giving a bell-shaped curve. And if we look at many bridges and see their tolerance distribution, okay, at what weight does the bridge give in? Does it break? That also is a normal distribution. Most of the bridges will have a tolerance value, okay, in a small range, and we can talk of a mean and standard deviation. Now we want the probability of damage to the bridge to be less than 0.1. How many cars can we allow to go on the bridge? So this is a practical problem which needs to be solved, and it illustrates the application of the central limit theorem. So when does the bridge break? The bridge breaks when the total weight on the bridge exceeds the tolerance level. Total weight is greater than W total is greater than W tolerance. Okay, so this is the governing inequality. Now we want the probability of this happening. Okay, W total exceeding W tolerance, the probability of that should be 0.1. So we want this probability to be very small. Now we can invoke CLT, central limit theorem. Okay, how? Suppose n is the number of cars which can be safely allowed on the bridge. what does safely allowed mean? The probability that total weight will exceed the tolerance level should be less than or equal to 0.1. So that is the meaning of safely allowed. Okay. And each car's weight is normal with mean equal to 3 and sigma equal to 0.3. So by the central limit theorem, total weight of n cars, okay, is also normally distributed. Okay, so that is the first part of the central limit theorem. And what will be the parameters of that? What will be the parameters of that normal distribution? The mean will be equal to sum of the means. So now each car's weight follows a normal distribution with mu, which is equal to 3. And so mu of the sum, okay, will be equal to 3n. And the variance will be equal to n into variance of each individual car's weight. Now variance sigma is 0.3, so the variance will be 0.3 square, which is 0.09. So the variance will be 0.09 into n. Okay? So I hope the setting is clear to you. N cars are now on the bridge. Their total weight has to follow a normal distribution. That normal distribution will have mean n into 3 and variance n into 0.09. So I hope the setting is completely clear to you. Is there any question or comment? Okay. So on the bridge, there are now n cars. And n is the value you have to find out. So the total weight of the n cars is normal with mu equal to 3n, sigma square equal to 0.09 n. Now W tolerance is a normal distribution with mean equal to 400 and sigma equal to 40. So the W tolerance, okay, the value at which the bridge breaks, is a bell-shaped curve. I hope it is reasonable and intuitive to you why that tolerance curve is a bell-shaped curve. Okay, you will not find many bridges with extremely high tolerance, very large tolerance. You will not find many bridges with very, very low tolerance. Now, most of the bridges will fall in a range with respect to their tolerance level. That's why a bell-shaped curve. So bell-shaped curve is a reality of life as we encounter in many, many situations: height, weight, income, and so on. Okay. So so we allow some risk. The bridge is damaged when W total is greater than W tolerance. That is, W total minus W tolerance is greater than 0. Notice that both of these variables, W total and W tolerance, both of them are normally distributed. Okay. And central limit theorem can be invoked again to say that this difference, W total minus W tolerance, is also normally distributed. Okay, so uh, you might ask, how does this follow from central limit theorem? Okay, we can prove this too, that the the difference of two random variables which individually follow normal distribution also follows a normal distribution. Okay, and their mean will be the difference of means, but the variance will be again will not be difference of variances, but sum of variances. Okay, all those things can be proved. So let's proceed. So we have to balance risk with resource utilization. Okay, if we allow very small number of cars to go on the bridge, then the bridge will not be optimally utilized. And if we allow very large number of cars to go on the bridge, then we have the risk of damaging the bridge. Okay, so we have to strike a balance between risk and resource utilization. We have to allow optimal number of cars on the bridge and give probabilistic bounds for this, and we would like to take some risk. Okay, so this is the setting. So, so we want the following. What is the number of cars that will cause the probability of damage to the bridge to exceed 0.1? Okay, so we want to work with this inequality. Probability of W total minus W tolerance should be greater than 0.1. Okay, so we want to work with this inequality. LHS is of n because is a function of n by central limit theorem. Now, what is the meaning of the inequality? Probability of W total minus W tolerance should be greater than 0.1. What is the meaning of this particular statement? Let us suppose n unsafe is the limit on the number of cars allowed on the bridge. Okay, so if you add one more car to n unsafe, then there will be damage to the bridge. So the meaning of this inequality, probability of W total minus W tolerance greater than 0.1, would mean this. Out of 1,000 cases of the bridge, allowing n unsafe cars to pass over it, in more than, should be 100, in more than 100 cases, the bridge will break. Okay, so probability is always a statement in the limit. So as we increase the number of cases, okay, as we increase the number of cases, make more and more observations, then probability actually begins to become realistic and begins to become trustworthy. This is also a consequence of the central limit theorem, as we'll see. So we have this common knowledge that as the sample size increases, as the number of experiments increases, we have more and more faith in the certainty factor, probability, and so on. Okay, so we are working with these inequality. So I have to make this correction here. Now, if we calculate these values deterministically, this calculation I am not showing. If we allow minimum risk and minimum utilization of the bridge, then the n safe value is greater than or equal to 109. And if we allow maximum utilization and maximum risk, then deterministic calculation again gives me the bound of 163. Okay, so those calculations we can see later if we do not allow probabilistic methods. Okay, you have been given the mean weight of 3 and the tolerance limit of 300, 400. Then you can make these calculations by taking lower bound on the car weight, upper bound on the bridge weight, upper bound on the car weight, lower bound on the bridge weight. From that, you can determine these numbers, 109 and 163. So these are extreme points. However, none of them are acceptable because 109 will not allow the bridge to be maximally used. 163 is also not allowed because that will definitely break the bridge. Okay, so the optimal value is in between. So we know that W total minus W tolerance is the quantity of interest, and this also happens to be a random variable following normal distribution. Of course, it is a random variable because W total and W tolerance themselves are random variables. But the interesting fact is that this difference also follows a normal distribution. So we have already determined the mean of W total. This is 3n. And the mean of W tolerance is 400. Central limit theorem tells me that for the difference of two normally distributed random variables, the mean is the difference of their means. And the variance is not difference, but sum of their variances. Okay, those things can be proved. So we have come this far, okay? And now we apply another machinery of probability theory, okay? Namely, converting any normally distributed random variable into standard normal form. So for obtaining standard normal form, we know we have to subtract the mean from the value of the random variable and also divide it by the standard deviation. Then we get a normal distribution whose mean is 0 and standard deviation is 1. Okay, just recall that this is what we know from the probability theory. Okay, so for standard normal distribution, the mean is 0, the standard deviation is 1. Okay, so now what we do is that we have this random variable W total minus W tolerance. This is the quantity of interest to us. This is a normally distributed random variable. Its mean is 3 and minus 400. Its standard, its variance is 0.09 n, 0.09 n it should be, plus 1600. Okay, and so this this operation is giving me a standard normal variable. Okay, just a second. Yeah, there should be an n here. Okay. So this change has to be made 0.09 n. Anyway, the process is this. So we want this probability that z is greater than minus 3n minus 400 by 0.09 n plus 1600 should be greater than 0.1. And by consulting the table of values for standard normal variable, I come to the value n equal to 117. So these details we will work out. Okay. So let's look at the standard normal form. And this is the table which we can read off. All these things we'll do. Okay. Now, before that, let's go into a bit of digression. Okay. And let us see the relevance to AI, ML, NLP. So far we have been discussing the concepts with the example of a bridge and cars going over the bridge, that problem. Okay, we are interested in the total amount of the weight that the bridge can tolerate, and that would be the sum of weights of cars. And since the sum of weights of cars is involved, we knew that central limit theorem could be invoked. Okay, now let's go to some NLP discussion. So we do this discussion with the help of language model. And this concept is the following. V is the vocabulary size, that is the number of unique words from the training data. And the bigram language model problem is this. Given a word W to the input layer, that means of a neural network, the network predicts the next word W text next. Okay, so this is of course independent of neural. So given a word W, predict the next word. This is my problem. Okay, in language model. This is the bigram language model problem. Okay, now traditional n-gram based language model, what will they do? They will compute probability of W next given W by counting the number of times this pair W and W next appears. Okay, so strong coffee, for example. I want to find out the probability of coffee given the word strong. Probability of coffee given the word strong. The probability of character given the word strong. Strong character. Probability of innings given the word strong. Strong innings. Okay, he played a strong innings. So I have to calculate the number of times these strong and coffee appear together next to each other, okay, in the corpus. What is the number of times W appears, strong appears, and take the ratio of strong coffee number of times strong coffee appears in the corpus divided by number of times strong appears in the corpus. Okay, so this is the probability computed. You can easily see that the number of parameters to be learned here is V square, where V is the vocabulary size, unique words. Okay, and the number of W will be equal to V. So this is order V square complexity. In neural language model, what will happen is that we have the input layer of size V, a projection or hidden layer of size D, and the output layer of size again V. So I give the input word W in the input layer, and I obtain the next word W next in the output layer. Okay, one of the neurons will fire, and this will become on. Now, what is the number of parameters to be learned here? The number of parameters is V into D. Okay, so many weights here, and also D into V, so many weights from hidden to output. So clearly the number of parameters being learned is order V. Okay, order V. Now, surely neural language model has many advantages. The number of parameters to be learned is linear in the size of vocabulary. Data sparsity problem is solved much better in neural language model. Okay. How? Because if you do not have a word in the corpus, you take its one-hot representation. So this one-hot representation will give activations to the projection layer by transmitting signal over the weight vector going from that neuron to this. Okay, and that itself will again fire one of the neurons here. Actually, it will fire many neurons, all the neurons, but they will have different probability values. Now you will get a suggestion. Okay, you will get a suggestion even if you have not seen the word. Okay, so that is the meaning of data sparsity being solved much better. You will get a suggestion anyway. But if you do n-gram language model based computation, then if the word is not present in the corpus, then the ratio of counts will not work. And this model is also more robust than n-gram language model. Okay. Why is it more robust? Because even if a particular weight value is wrong, okay, wrong in what sense? We have to say that later. Then this operation of the neural network doesn't appreciably degrade. But in case of n-gram language models, you do see that if parameter value is wrong, then the ranking can go completely, the ranking can be very different. Ranking means suggestions for the next word. So the next words are suggested by means of a ranking, and it is based on the ratio of these counts. Now, if there is mistake there, the ranking will get disturbed. That is not so much the case in case of neural language model. Even if a single weight is wrong in whatever sense, the suggestions will not change drastically. I thought I saw a question on the chat box. What was that? Was there a question on the chat box or a comment? Am I audible?
There's a question by Kaveri which says we are considering multiple bridges, not single bridge, hence W tolerance is random variable. Is this interpretation correct?
Yes, yes, yes. So W tolerance will vary from bridge to bridge, but it will be normally distributed. Okay, so this is the neural.
Then there's a comment by Swaroop.
Yeah.
It says it can be non-deterministic even if we take a single bridge. Usually these bounds are determined by manufacturing or assembling process, materials used.
That is true. Yeah, that is true. Non-deterministic means, so I don't know how correct the term non-deterministic is here. The fact is that the tolerance value will be in a range from bridge to bridge, okay, but it will follow a normal distribution. Now comes the question, okay, which probability will you trust? The ratio of counts from corpora or the softmax probability at the outermost layer of feed-forward neural network? Okay, being students of NLP, have you thought about this question? Which probability can I trust? Okay, I find out the ratio of strong coffee with respect to strong character, again with respect to strong innings, okay, strong views. I find out the ratio of all these situations, and whichever probability is highest, I will suggest that word as the next word. Okay, so this is one method of getting the next word. The other method would be that I'll take this neural network, take the SIBO or skip-gram model with input going to context or context going to input, and I'll take the suggestions from the outer layer. Okay. And these suggestions, of course, will have probability because at the outermost layer, you are computing softmax probability. Which probability will you trust? Okay. And if the ranking is different, as suggested by neural versus n-gram model, which probability will you trust? Okay, that's a question. Let's keep in mind, and we'll see that again. Central limit theorem will be of help here. All right, so let's go back now to our bridge problem, and we said that we have converted the difference of total weight and tolerance into a standard normal distribution. So let's look at the properties of the standard normal distribution. Standard normal distribution has mean 1 and standard deviation 0. Now, there is a very important concept called Z-score. Okay, I'm revising your concept of probability, or maybe I'm introducing some useful probability concepts. Z-score is the area under the curve from minus infinity to Z, okay, to some value Z. The capital Z is the random variable with respect to a standard normal distribution. So capital Z, okay, capital Z follows normal distribution with mean 0 and standard deviation 1. So Z-score is the probability of Z being in the interval minus infinity to small z. So capital Z is random variable, small z is the Z-score. Now we know that any normally distributed random variable x can be converted to standard normal form, and that is depicted here, z equal to x minus mu by sigma. Now, interval probability is integration or the area under the curve from z equal to a to z equal to b. Now, area under the curve from a to b is the probability of the z being in the interval minus infinity to a and subtracted from minus infinity to b. Okay, Z-score, remember, is always from minus infinity to a particular value of z, always. Okay, so z equal to small a to z equal to small b, this area you can find out by integrating the density function of standard normal distribution from a to b, but that integration is cumbersome. Okay, what people have done, what statisticians have done, is that they have given you Z-score tables. And these tables give you values from minus infinity to a particular value of Z. Okay, how to read the Z-score table is also instructive. Students of probability should learn this. Now, since Z-score is always given from minus infinity, you can see that obtaining the value of the interval A to B is Z score at B minus Z score at A. Okay, and fortunately for us, Z score at B and Z score at A for various values of A and B are given in the form of a table. In the form of a table. Now, the probability of the standard normal curve area lying under minus infinity to B is 1 by root 2 pi exponential of minus y square by 2 dy. Integrating this is non-trivial. Okay, it is very difficult to find out the closed form algebraic expression. So instead, we work with what is called the Z-score table. I hope the screen is visible to you and the numbers are somewhat readable. Okay, so if I want to read this table, for example, let us see if we can verify some of the things we know. For example, the value of the normal curve, okay, from minus 2 sigma to plus 2 sigma should be equal to 95%. So minus 2 sigma to plus 2 sigma. Minus 2 sigma is minus 2 to plus 2. Okay, so let's see if we can read minus 2 to plus 2, which should be about 95%. Okay, so at from minus infinity to minus 2, the area is 0.0228. Okay, the area is 0.0228, minus infinity to minus 0.2, minus 2. Okay, so now let's see if I can also read of the area under the curve from minus infinity to 2. Yes, so that area is 0.9772. Now, if I subtract the z-score at minus 2 from z-score at 2, I will get the area under the curve from minus 2 to 2 plus 2. And we know that approximately 95% of the area is minus 2 to plus 2. So let's see, is it so approximately minus? So if you subtract 0.0228 from 0.9772, you will get about 0.95. Okay, so this is how one reads the Z-score table, an extremely useful tool for probability and statistics. So any question on the Z-score table? This is going to be important for us for hypothesis testing. Any question? So you see there are rows and columns. So the way to read is, so let's say I want to know the Z value up at 0.9. So then you see, take the row 0.9 and then the column 0.00. Okay. What about 0.91? You take the row 0.91 and go to the column 0.01. That the area is 0.8186. What about 0.92? 0.9 row and column 0.02. This is the way the Z-score table is read. A very, very useful technique for probability. Any question how to read the Z-score table? Okay. Any question on the chat box? Sandhya?
No, sir.
No. Okay. So this is the way to read Z-score table. I'll just say it for the last time. That the Z-score values are always given from minus infinity to the value of Z. And the values of Z are given in a somewhat peculiar way. You can take decimals up to 2 places. The rows are for the first decimal place and columns are for the second decimal place. So whenever you have to read a value, go to the row corresponding to the first decimal place and then go to the column corresponding to the second decimal place. Okay, the number which is given there is the z-score value, and the z-score value is from -infinity to that z value. Okay, so it is important to learn what is a z-score and how to read the z-score table. Let's go back to our bridge problem now. Okay, now we have seen that W total minus W tolerance is a random variable. The mean is 3n minus 400. Variance is 0.09n plus 1600. Okay. So this also needs to have an n. Okay. Now W total minus W tolerance should be greater than 0, which means this quantity. Sorry about that. Okay. And this also needs an n. Okay. So I hope you understand how this is coming about. So W total minus W tolerance minus the mean divided by standard deviation should be it should be greater than this quantity. Okay, and this is coming because of this equation. Okay. Z equal to W tolerance, W total minus W tolerance minus mean. Okay, then probability of this standard normal variable becoming greater than this value should be greater than 0.1, and that will so this is the area under the curve. Okay, so here we will have to apply some amount of numerical technique. Also n. Solving this will give us n is less than or equal to 117. Right. So now probability greater than 0.1. Okay, probability of z greater than b becoming greater than 0.1 is 1 minus probability of z less than point b should be greater than 0.1, or probability of z less than b should be less than or equal to 0.9. So all these are algebraic manipulations which lead us to the value of n by reading of the z-score table. Okay. So now this is the way this is done, and what we have learned today is the statement of the central limit theorem, the concept of standard normal variable, that is a brushing up, and how to read the z-score table, okay, consulting the rows and columns. And we also know that there are important intervals under the standard normal curve, which are going to be important for many, many applications. Okay, and the relevance to AI/ML NLP is that we have to invoke probability many times. Let me finish with another situation, the machine learning based part of speech tagging problem. So there is also a risk versus resource trade-off. Now, risk versus resource trade-off in machine learning is also called the false positive, false negative problem. So if we had infinite amount of annotated data, and if we record every possibility in a table, okay, then a new sentence will just do a table lookup and do a matching. So you see, this is infinite amount of annotated data. Infinite means every conceivable sentence is there in the annotated data. So whenever a new sentence arrives, it must match one of the annotated sentences. And we simply look up the annotation which is given in that sentence and propose that as the pause tag sequence for the new sentence. So this is the meaning of infinite amount of data. But we know that infinite amount of annotated pause tag data is impossible. It will be very costly in terms of resource. First of all, it is not attainable. Infinity is not attainable. And doing part-of-speech tagging annotation is an expensive proposition. So if not data, then what can we do? We know that whenever we have short supply of data, we have to pick our brain. We have to go to knowledge. And then we will have to create a rule-based system. Now, again, rule-based systems will possibly need infinite number of rules. Okay, that possibly is a loose statement slightly, because you have to anticipate all possible situations for part-of-speech tagging. This will need huge amount of language insight and a lot of linguistics. That generalization is also not very trivial, and thereby this will also be very costly. Okay, and we know that rules cannot anticipate all possible ambiguities, and rules fire in many different ambiguity situations. Then there is a matter of which rule to prefer over a number of rules, which rule to pick for firing. So again, there is a probability situation coming in. So we take risk in the sense of the breach, for example, breach breaking. Some reasonable amount of pause annotated data is taken. We train a classifier, hidden Markov model, or support vector machine, or a deep neural network. We allow for mistake. The breach collapsing, for example, was a mistake. Then the automatic pause tagger will make mistakes, surely. It will go wrong a certain number of times. We want to minimize that mistake probability, just like we want to minimize the probability of the breach breaking. Okay, so we should be able to give probabilistic bounds as to how good our part-of-speech tagger is, just like we could give probabilistic bound for the breach tolerance. Okay, if you allow 117 cards at the same time on the breach, the probability of the breach breaking is not more than 0.1. So that kind of probabilistic bounds can be given in any kind of machine learning situation, including natural language processing. So this is how we will proceed. And in the background or at the foundation, there is always this central limit theorem at play, because we will have to always work with sample and make claim about the population. Only the central limit theorem will allow us to do this. Okay, so we'll continue with central limit theorem, bringing in lots of NLP machine learning situations, but we want to understand the central limit theorem in totality, all its nitty-gritties, and acquire the machinery of probabilistic analysis. One is this Z-score reading. Then moment generating function is something we'll learn in the next class, and give a proof of central limit theorem. Okay, so let's be very, very rigorous when it comes to probability. Okay, I'll end today. Now, is there any question? It's exactly 11 o'clock. Any question, comment from anybody? The recording will be available, and the slides, I think we are keeping on CField. If not, we'll make that arrangement. Do take a look at the slides and look at the recording. Any question on the chat box in there?
No, sir.
Okay, any doubt from anybody? No? Okay, so let me finish the lecture with one statement. The sum of normally distributed random variables is also a normal distribution. Okay, remember this. Okay, thank you.